no idea what you were. I'm not thinking of it.
The topological sort?
Yeah.
Didn't think it would work.
And I thought it did, but just the way it didn't seem intuitive to me. But I guess it did.
I guess it's crazy because I just thought of it as a map. Every vertex is now just like a public.
Right, you are being recorded, just so you know. Where is everyone? I'll go bring some more. Okay, thanks.
Hey, you're the one to say.
No, then you repeated it about 5 times.
It's not why. Like, not for absolutely anything, right?
Hello. I don't know what to do now. We're not ready. We'll just pick up.
Can we see the results now?
I think they typically freeze it after the contest. After the contest.
Okay.
Is that sure? Oh, yeah.
We top 50 guys.
I don't know about that.
I think so, probably.
We were top 37 pros.
We peaked at 20 at some point, right?
Yeah, we did.
I think they're at least bronze,
What's bronze?
which is top 50. That's cool.
That's how I know we couldn't get it.
It's a good start. Good start.
So I think bronze is going to be about 50, silver's like about 25, and gold is top like 8.
How was
Yeah, it's pretty impressive.
And it's bounded by.
Hello, welcome all.
Yeah.
Anywhere, grab a seat, do whatever.
My first comp, I got like 1 question right.
And it's like much bigger.
And it has to be in order of where it's almost 10v6, so n is almost 10v3. That's so cool.
Oh, they didn't give a bound for n, did they?
They gave n was bounded the same thing as n, but implicitly that means that n is bounded as where. Bro, I was correct about it.
That's too good.
I'm so annoyed about that.
Oh, Scott.
Well, at least welcome. We'll get started soon. Yeah, front row seats. That's good.
Oh, what?
How did we go yet?
Oh, 35.
You did the whole thing without me. Right? I think that's like.
I think you.
Oh, are the results released?
Yeah.
Okay, yeah, results are released, everyone, if you want to check how you did after the.
Preliminary.
Oh, okay, no, that's not final then. Yeah, okay.
Exactly. So it would be cool.
I probably can unfreeze them.
Oh, we are for one.
Not for me.
You get so much out of the body useful stream.
Hi, Eric.
I really like
Couple sorts of tops. So yeah, it has been released. Yeah, but like 279.
No, okay, so it has been full sold.
Who's the UTS team? Nothing.
Oh yeah, got full solved. Got full solved by 2 teams. Congratulations, those teams. The table flipping team and sometimes I drink barbecue sauce in my nightmares. The 2 full solved. Both fantastic names.
They're another UTS.
Yeah,
Oh, it's 6% Did you guys, do we top this?
I think you got,
No way, are you serious?
UTS with the units.
Like my second time.
That is true.
That is true.
That is true.
I invested.
Oh, yeah, can someone let them in, please?
Yeah, what the units?
Every
3 teams.
What problems did you guys like? What problems did you guys hate?
I'm UTS for the
We didn't do that many.
You think I might say it? If I say I'm doing this, I'll be
fun. I mean, it's still good practice.
Yeah, multi-threading.
We weren't allowed.
That's me for like everything.
I mean, it's just a practice contest. The more practice, the better. Yeah.
Oh, GG, bro.
Yeah, it's already.
You guys think I'm still?
I'm waiting in the lobby. I don't know how to let them in.
Are you host?
Like, no, this is just my personal laptop. I'm not doing anything on here.
Oh, you can go over there and let them in.
Oh, yeah. Awesome.
Yeah.
We can decide. We can decide.
I don't know if Ravine's coming back.
These guys teams are going to look.
I don't know if we need Ravine. Maybe. We don't need him. We can leave him.
I think me coding worked well. I think me coding worked well.
Sorry, I really don't.
And you, feel that, yeah, it's good. Everyone's doing great.
Yeah, let's go.
It wasn't the end of many spikes. So the limiting, like the deleted the policy and the input. Why?
Did you guys
On vacation.
Yeah.
Okay, I think we have lots of people here, so we can get started with the editorial now, in case you guys are wondering about the answers. Now, if we didn't get the chance to meet today, my name's Tom, Tom Frew. I'm running all the SPARs for this year as part of the South Pacific Programming Association. And yeah, I mean, it's been pretty great so far. Thank you all for coming to our contest. And we're going to go through the solutions now. I'm going to take you through some of the easier ones. I might ask some of you guys to take us through some of the harder ones if you feel compelled to share your thoughts, or you want to just chat about how you feel about the problem. Any contributions are very appreciated. But let's start with the first one. Now, I would say the easiest problem in this set is keeping sheep. So your opponent has bid C coins and you have N coins, and so you get your opponent's sheep if you bid more than them. You lose if you bid less than them, and if you bid the same as them, nothing happens. This problem is pretty trivial. If you have more coins than they do, then you should always bid above them, get a sheep from them. You want sheep, they're great. If you have the same number of coins, then to avoid losing one of your sheep, you should bid the same as them. And if you have less coins than them, then you should bid 0, because then you won't lose any of your coins. Very simple. The next easiest problem, I would say, would be problem D, which is Dralimpome. So a word is a Dralimpome if there exists a permutation of its letters that is a palindrome. Now, palindromes are mirrored words, so each letter must occur an even number of times. Obviously, the exception is if the length of the word is odd, the character in the middle is can occur an odd number of times. So simply count the number of occurrences of each letter and check if they're all even. However, if there's an odd number of characters, then you can have at most one odd. And you can simply do this with a hash map. So then time. And I don't know if you noticed all the Dralimpomes in the problem statement. There are quite a few to look for, but they're pretty cool.
I did not.
Now, the next problem we can go through is a bottle of Newport, which I believe is a reference to last year's contest with a problem called Battle of Newport. So we want to compute the alcohol content in a bottle after D days, or specifically the alcohol concentration. So we know the alcohol and the other stuff in the bottle, they both have various evaporation rates. You can simply sort of figure out how much alcohol and other stuff the bottle lost over that number of days, keeping sure to not make that negative. You've got to clamp it to 0. And then you can compute the difference by x divided by x plus y, where x is the amount of alcohol, y is the amount of other stuff. Some common issues in this problem, stuff like not converting to floats when you're doing your concentration calculation. In C++, if you divide two integers together, you're going to get an integer result, and it's going to round down. Stuff like that. That's very important. Also, long longs to store large pieces of information. Not necessarily for this question, but that was another very common issue for this problem. For this contest. The next problem was H, which is hidden sequence. So given 3 partial sequences of game winners, each missing one of the 3 players determine the full sequence of winners. And I think this one actually has a very sort of elegant solution. So for every game, even though the winner does not necessarily list their name, the other 2 players do append the winner to each sequence. So if you're reading the sequences all simultaneously from start to end, the sort of 2 top players, also the sort of, what am I trying to say, the latest winner is going to be agreed on by 2 people. And, the latest winner, the majority is going to be that one. So for example, if we were to have something like, I don't know.
Built a whole topo ground.
Something like this. At the start of the game, we know that these 2 won were agreed upon by the winner. So clearly, player 1 was the winner. So the first winner was 1. Then we can remove these from the set. And now we have these two as the next winner. So we know that 2 must be the next winner because 2 doesn't report themselves. So we can take that off the top. And then we have the 2 3s at the end. So something like that. You could, simply keep a queue of the winners. Check the top ones, find the majority, pop them off, repeat. Now for problem J, this is journal publication. Is it possible to pick a name part for each author such that the list is sorted? We have a list of first name, last names. It's always optimal to actually pick the lexicographically smallest name part that is still allowed by the previous part, because that's going to be the least restrictive for future authors. So for each author in order, we can determine the appropriate name part in linear time with a running minimum. That's pretty simple, and just create the ordering of them. Now I might start getting you guys to perhaps explain some of these. So does anyone have a solution for E, entropy evasion? Go ahead.
Okay. Yeah, the way I thought about it was expected value. So like if you have an array that's completely zeros, the worst that can happen is nothing, and every one that would get flipped is better than the other. So at any point you find the largest subarray with the most amount of zeros, and you do that, and that led to the solution for me.
Yeah, excellent. Oh, thank you. Oh, we got hella markers now. We have so much freedom. Yeah, fantastic. So yeah, you find the largest string that maximizes the expected gain, and you can use some. You can calculate the prefix sum of all expected gains to find the maximum string for that. And yeah, you can also brute force it. You may potentially be able to get it fast enough.
Was that largest subarray with like the most?
Largest subarray with like best expected value, so largest proportion of zeros.
Right, that is
Yeah. Okay. Does anyone want to explain problem G? I know this was a contentious one. Yeah, please go ahead. If you want to come up or just like speak quite loudly, that's up to you.
Okay, like when it says like A is the son of B, you can pretend it's an edge from B to A. And so I can do a graph. Rule is that it's possible if there is at most one node with no integrity. And if you treat the edges as undirected, there should be exactly one component. And so if there's 2 components, it's like trivially not possible. And if you have 2 nodes with 2 or more nodes with no integrity, then they'll have to be the roots of 2 different trees, so it's not possible as well. Otherwise, if it's true, you sort of construct the tree, but you take your node with no integrity, or just pick any other random node if that doesn't exist, and you like to DFS in the graph from that. And so in the DFS, you'll like walk down every edge, and as you walk down the edge, you can sort of like clone the endpoint if you need to. I can construct the tree, a bad tree that way. We don't have to do that because you just need to print yes or no. So yeah, that's how you solve it.
Yeah, I think there was a very important trick here for this problem, which is that, if you have A, which is connected to B, which is connected to C, and back, this is actually okay because we can just take any one of these and pretend they're 2 different people. So you have A1 to B to C to A2. And these 2 A's, they have the same name, but we can treat them as different people because in this question, we can interpret the names as either the same person or different people, depending on what's the most convenient for us. Yeah, great explanation. Okay, does anyone have one for I? Sorry, what was your name? Michael?
Miles.
Oh, Miles. Nice to meet you, Miles.
Okay, so we have some sort of array that's monotonically non-increasing, except that some of the elements are unknown. And we have to find for each unknown element the possible ranges of. So we are going to extend this by setting the unknown values to some value such that this array remains non-increasing and that the total values sum to 100. And for each value, we need to find the possible range of valid things. So for instance, in the case where we have, this is worth 80, and then we have two unknown values. This thing in the middle could go all the way up to 20 because 80, 20, 0 is valid, but the minimum it can go is 10 because anything less than that, the thing on the right would be too small. Whereas on the left, we have the range 0, 10. And so what we can do here is first, we can assign for each unknown value a strict minimum and strict maximum by just running some sort of prefix min and prefix max. And we know that for each value, we can constrain its range as a subset of this. So we have two slightly different algorithms for finding the minimum and the maximum. For finding the minimum, we first set everything else to its theoretical maximum value, except we constrain everything to the right by this thing's lower bound. So for instance, if we are trying to determine the minimum of this value, and let's say that is 10, then we would set this to 10, this also to 10, and then this to whatever the upper bound of this is. So if that is larger, we use this upper bound. So now we have some sort of sum of weights. If this sum of weights is over 100, then we can reach 100 by just decreasing the later ones, and therefore the minimum possible value for this is its lower bound. Otherwise, to increase it up to 100, we have to increase this value, and the minimum that we can increase it by is going to be the deficit, so 100 minus the sum divided by the number of things downstream that we're able to increase, which is going to be the distance to the next constraint one. So in this case, suppose our deficit was 12 because we have these two objects in the way. We had these two objects before this in the way. We divide that by 2, and so the maximum will be this lower bound plus 6. To find the maximum, we have a very similar case. We instead try to minimize everything by setting it to its lower bound. And now we want to find the maximum amount that we can increase this such that it doesn't overflow the rest. Because if we increase this, we might need to increase everything to the left. And this is just going to be the remaining stuff. So 100 minus the sum divided by the number of things that we can move on the left. So for instance, if our total sum from minimizing everything in this example is going to be 30 plus 20, 20, that is 0. So, okay, that doesn't work. Let's say that's 25. Our sum is 95. And so for this, we can increase it up to 5 while still remaining a sum less than 100, or this up to at most 2.5. One possible pitfall here is that you also have to check that you're not increasing it past the upper bound. So it just becomes the minimum of the upper bound and this thing. And n in this case was like 100, so you can implement this as inefficiently as you want, it still works. But you should be able to get this in O of n, I think.
Yeah,
You just do a bunch of swing lines.
Yeah, excellent. That's very well explained. Does anyone else want to go through the next hardest problem, which is A, auto adaptation?
It's just That's what I was saying. I was like, once you get this.
Thank you. I was trying so hard to figure out how to explain it. So you gave me the trouble.
So on A and
Just like.
What is that? Did you want me to get you an eraser? I think I saw one over there. I'll see if I can find one.
On every question, they also force off.
It would be right. I think there's some more space over here if you want it. I know. Stop. Oh, really?
Like think about it.
I'll fit my thing on this.
Yeah. Okay, that'll be good.
So you have n nodes and you have an L and H. L is, I guess, your lower bound for
Yeah.
You also have a bunch of nodes. And you're trying to move them one octave up or down, so they fit into your code house, or not one, but like multiple of default, because apparently there's 12 nodes in one octave, which is what I learned today. So you can sort of think of, so we're trying to group them together, and we can sort of think of, we can group two nodes together if they share, if we can think of each node as having a set of possible ranges where they can move up to the octave. So let's say this is 20 and this is 20, and your node A is X. A can move one octave up to go into our range, or it can move 2 octave up to go into our range. So in this case, that octave set for A would be either 1 or 2. And if it was like 41, for example, then the octave set would be like -1 or -2. Which is nice. So which is nice. So we can transform each node into like a list of octave sets. Then we do a DP problem. So our subproblem is given our list of octave set and index I. What's the maximum of the minimum choice within this? And to solve the problem, you first consider A as its own interval, and then you do that subproblem for B and the rest, and then you try to add on B, and you can add on B only if A and B have a non-empty intersection set between the octave set. And then you solve it for C and the rest, and then you add C if A, B, and C have a non-empty intersecting set, and so on and so on.
Yeah, no, that's very good. Yeah, nice work. And what's the time complexity?
Probably O(n) squared is n subproblem, and every time you solve a subproblem, it should be n.
Yeah, that's correct. For each, you might have to look at all the previous ones. Yeah, briefly, you might have to consider all the variables. N squared is correct. Very nice. All right, good job. All right, I know I'm saying this about everyone, but this may have been the most contentious one. This is friendly formation, problem F. Does anyone want to take us through this one?
He does.
I could have been straight on.
Yeah, if you can, that'd be good.
We didn't even look at these questions. Like,
Okay, so for this problem, you want to split the graph into two sets of size n over 2. But within each set, it's a sleep, so every edge exists. I think that's the entire statement. And so the first thing you can observe is that since the cap on the edges is 1 million, if the number of nodes are too large, then it's like trivially not possible because there aren't enough edges to do, right? Like if you have n is 5, so n is 10, then you know the two halves will be 5 each, and that would require like 20 edges. And so you can plug in an easy bound of like n is 3000, then you just create it impossible because you know for sure you won't have to play it anyways. So we'll assume n is like almost 3000. Then afterwards, the problem's easy to think about if you consider the complement graph, because for some valid solution, if you take the complement, then what it becomes is the regular bipartite graph, where either half is size n over 2. And if you consider the complement and construct some bipartite graph, n over 2 like uncomplemented, it's like valid. So it's an equivalent problem. So we take the complement graph. It's like you can construct it directly because n is like 3000 now. You can afford to make n squared edges. And so we're trying to partition this complement graph into two sets of size n over 2, such that all the edges go between the two sets. And so then you can DFS to find connecting components. And for each component, you'll have like the red and the blue nodes. And basically, for each component, you have to assign either the red set or the blue set to be on the like left or right half, let's say, in your final solution, right? Because like for each sort of component, you can eclipse the colors and assign them opposite sides. And so from this point, each component has some number of red nodes, some number of blue nodes, and you want to figure out if you can, for each component, pick one of the red or blue colors and make it so that the sum is n over 2, right? You sort of want to, so it becomes like a knapsack problem. And so since n is 3000, you can just run your like n squared knapsack and then reconstruct it to figure out a valid assignment. I know how much sense that last part made.
No, makes sense. Yeah, you either assign one part of a bipartite graph to red or blue, and it's just knapsack. Try to get the right numbers. Yeah, very good. All right. The next problem is Landgrave. All right, so for problem L, which is Landgrave. So we have some number of points, and we want to connect some set of them to create a polygon that has no interior angles less than 90 degrees. So I put this one up higher here. Now the solution of this one is really quite simple. We get the convex hull of the point. And we can check if this is a valid solution by checking every pair of adjacent points. If it is a valid solution, then we're happy. If not, then there is some angle which is less than 90 degrees. But if there is an angle less than 90 degrees in the convex hull, between these 2 points, it's also less than 90 degrees to all the other points. So, to this one over to that one, to this one over to that one, to this. Essentially, what I'm saying is it couldn't possibly be part of any solution we create, even if we delete other points. So what we can do cut it out, redo the convex hull. And now, in this case, we're happy. And that's all there is to it. And this is proven to be optimal. If we end up with fewer than 4 points, obviously triangles can't have interior angles of 90 degrees or greater for all of them. So then it's impossible. And we need the n log n algorithm for convex hull so that we are able to get a total of n squared log n. Because we may need to reconstruct the convex hull for every single point we delete. I think that's all. Yeah. You think it's too slow. Okay, the last problem is problem C. We had a lot of really great solutions to this one at the last seconds of the contest. Does anyone want to explain how C works? This is the calculation syntax part. Go ahead. Good job, by the way, getting it.
Yeah, for this one, I sort of kind of thought about for one a little bit, where we did like this context-free grammar stuff. So basically, one way you can think about it is you have some expression. You want to think what's all the different things it could be within the rules that you're given. It's allowed to be like a variable, or it can be like the sum of two expressions, or it can be like the product of two stuff, but those two stuff kind of have a special condition that they have to be like, I just use the word closed, where closed means it's either like just a variable on its own, or it's the sum of two expressions, but in brackets. That's because like when you multiply it, you want to make sure like the whole thing is multiplied. Or it could just be the product of two closed expressions as well. And so this is sort of what you end up with as the rules for something which is valid. And now using this, we want to basically see what all the different strings we're allowed to construct. There's a few like kind of obvious rules you can figure out from doing this. Like one obvious one is obviously the brackets have to match, same number of those. You can also see every time you add a left bracket, you also add a plus, right? So that's another condition that this is equal to that. And the other thing was like with multiplication, basically every time you add a parenthesis, you're going to have to add some operators, including at least one plus. But you want to sort of minimize the number of multiplications you have to do, because one option you always have, if you have spare multiplications at the end, you can always just add them at the end as like times something. Also, another observation is like the number of operators is equal to the number of variables plus one. Or maybe the other way around. The number of operators plus one is the number of variables. Hopefully that makes sense, because every time you have an operator, it's separating two stuff. When I say variable, I'm referring to like either a number or like a letter followed by some numbers. You can basically think of them the same.
Can you have more letters than operators?
You can have more, because if you sort of like have some expression, like for example, this thing plus that thing times that thing plus that thing, you need to have at least as many letters as these blocks. But if you have more, you can always kind of just dump them on the last one, right? Because like if you have like V over there and you have some extra letters, you just chuck on the end. There's one exception to that, which is if you've got only the zero character, then you're not allowed to dump extra zeros on the last zero. So it's like a special case you also have to deal with. If it's all zeros, it has to exactly match the number of blocks. Yeah, otherwise, we sort of did a bit of experimenting, and kind of just by following this, you can sort of see that the maximum number of brackets you can produce with a single bit of multiplication is to sort of do this formation, like that plus that, where we essentially use one multiplication to create two pairs of brackets. And it's somewhat easy to convince yourself that you can't do better. And so you could also then take this guy and replace it with the same version. And that basically means that the number of multiplications you have has to be at least the number of brackets divided by 2. It also has to round up because if you've got like an extra odd pair of brackets, then to sort of finish it off at the end, you still need to multiply by another one of them, kind of using that thing. So this is a bound, and you have also these other bounds. And then from this, you sort of construct your general thing by just building this thing, and you can just replace this with some letter. I chose to nest with this one because it's probably a bit easier. So you just put some letter here, some letter here, letter here. And then this one, if you've still got plenty of brackets left, you just repeat the same thing, kind of recurse down and do that. And then after you do that, because the recursive part only adds pairs of brackets, if there's another one that you need to do, you just slap it on the end. And then at the end, you can just do like times block, and then plus block, plus block, plus block. It's a few like finicky stuff as well with like making sure you can add all the extra letters. Because like we had an issue where we thought like you could just add them to the end. But one thing that's important is when you're filling out the stuff, you don't want to end up with all zeros at the end because you can't put a bunch of zeros together. So we made it so you put the zeros first and then the variables last. But you don't want to, what's the issue? You can't have it be like a number and then a bunch of letters. And so the last one, we just reversed it. But to first reverse it, you can also run into the case where the last one is actually inside some brackets. So you also have to pop off all the brackets at the end, then grab the last part, swap it, and then put all the brackets back. Yeah, that's pretty much it.
Yeah, fantastic. That was an excellent excellent explanation. This is a very observation-heavy question. A lot of things that can go wrong with trial and error. But yeah, I think your core idea of like getting rid of brackets as efficiently as possible with that structure is really the key to it. So yeah, excellent work. Yeah. And I think that's it. Yeah, that was a pretty quick editorial. Thank you everyone for attending. If you're interested in studying these problems a little bit more, they are taken from the Bella-Lux Algorithmic Programming Contest, or BATC, 2025 preliminary finals. So this was the prelims for the Belarus, Netherlands, and Luxembourg ICPC. There's some nice diagrams in there for you to have a look at if you need some more sort of intuitive understanding of some of the questions. And there are a lot of observations they talk about things that people often miss and stuff like that. And I'll probably post that on the SCPCA Discord server or some other places that you guys are figuring out. Yeah, the solution, it's not the solution. I mean, the solutions are released, but the leaderboard is also released. So if you want to see how your team ended up in the end, you can have a look at that. Roughly the top 1/12 are going to get gold medal for this one, 1/6 silver, and the top 1/3 after that is bronze. Yeah, if anyone has any other questions, feel free to chat to me. Otherwise, thank you all for attending and have a nice night. And do echo tonight.
No, I was giving you a resource. But like, why are you forcing it? Oh, I mean, look, I'm pretty on it.
Oh, you know, different thing.
Yes, bro.
I
actually saw that.
Yeah,
I mean, you saw that deep. But it wasn't.
Push down his